Now that you've had so much practice creating two-dimensional Lewis structures, it's time to finally consider molecular shape and the overall three-dimensional structure. And this is all based on the valence shell electron pair repulsion theory, which sounds a lot more complicated than it really is. This theory is based on the idea that valence shells on the central atom are going to arrange themselves in a three-dimensional space that will minimize electron-electron repulsions. Remember, by minimizing these repulsions, we are assuming the most stable, low-energy configuration. Electron groups are defined as groups of valence electrons that are either lone pairs, bonding pairs, or multiple bonding pairs. So if we were to say carbon being a central, this is an electron group. This single bond would be an electron group. And even double and triple bonds would be considered electron groups. I'd like for you to get out your shape sheet, and we're going to be using this throughout the next several videos as we begin to explore three-dimensional shapes along with ideal bond angles and chemical reactivity like polarity and hybridization. Now, here we have electron group shapes. Now, as I mention and go through these, I want you to look at your shape sheet. Electron group shapes are showing the shapes that the electrons will arrange themselves in depending on the number of groups. And we have just defined electron groups as lone pairs, single bonded pairs, double and triple bonded pairs. All right. So there are a total of 5 electron groups. All right, so starting with 2 groups, we have linear, then we move to trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. We're going to denote the molecular composition with an AXE designation. The A is representing the central atom. X is the surrounding atom or atoms, and E would be non-bonding valence electron groups. Those are going to be your lone pair of electrons. M and N denote the integers, so the number of surrounding atoms, the number of lone pairs. So let's look at your shape sheet here and identify the AXE designation so you can familiarize yourself where to find that, and also take a look here at something called the molecular shape. Okay, the molecular shapes are determined by the interactions of lone pairs and bonded pairs. All right, this is going to define your geometry and what I will call the ideal bond angles, because as you know, there are exceptions when we're dealing with such complex interactions. All right, so we have defined electron group shapes. There are 5. And now there are molecular shapes or molecular geometry, and there's a whole series of those that I'm going to discuss over the next couple of podcasts. Let's start with the simplest configuration, AX2. Recall, A would be your central species, X would be your bonded pairs. Okay, so this will be really the simplest that we can have. All right, so I want you to copy down several steps here. Step number 1, follow all the steps in the previous video for determining the Lewis structure. Okay, so all of those that we outlined, including formal charges, go through and do that for each molecule or compound. Step 2, count those electron groups. There's a couple synonyms here. Electron groups may be referred to as effective pairs and clouds. So if I ask you to say, count the number of electron clouds, I could also say groups or effective pairs. In this case, we're dealing with 2 electron clouds. All right. And next, step 3, determine the number of bonded pairs and lone pairs, and use your shape sheet to find the molecular shape and the ideal bond angle. That's as far as we're going to go in the next 2 videos, okay? So, again, you're going to go through and find the number of bonded pairs, and remember, that could be a double or even a triple bond, counts as 1 electron group or cloud or effective pair. Then your lone pairs on the central atom count as groups. If there are 2 lone pairs on a central atom, then you have 2 electron groups or clouds or effective pairs. Let's do some examples here. Example 1, let's look at beryllium chloride. And I would encourage you to pause the podcast and go ahead and try this on your own throughout the entire video. Okay, so beryllium chloride. Beryllium chloride. So you're thinking right now of all those steps where you're adding up all the valence electrons, and then you're making your skeletal structure. Then you are going to add remaining electrons to the outer or ligand species. Then you're going to do all your checks. Have we satisfied the octet rule? Have we violated anything as far as formal charges are concerned? And in this case here, beryllium is one of those exceptions that I discussed in the last video. So beryllium is an exception, all right? And beryllium here, if we look at formal charge, valence electrons 2, number of bonded electrons 2, that's going to give me a formal charge of 0 here, 0, 0. So I'm combining what you learned in the last couple videos and putting that out there right now for you. So beryllium is structurally satisfied, and this is the lowest energy configuration. So if we were to count the number of electron groups, we have 1 electron group, 2 electron groups. There are no unbonded pairs or lone pairs on the central atom, and we're only concerned with the central atom. So I have 2 groups, 2 electron pairs, 2 clouds, 0 lone pairs. This is a linear shape, okay? A linear shape, just like a straight line on a sheet of paper. And I'm going to talk about bond angle here in a minute. Let's do another example. Let's do carbon disulfide. Carbon disulfide. So you're going to make your skeletal structure after you've added up all of the valence electrons. And once you go through and start making the structure, you're going to find that you're going to actually need double bonds on both of the outer. Notice again, the most electronegative species are on the outside of the structure. The least electronegative are placed in the center, okay? When you go through here and look at this structure, you'll find that formal charges are equal to 0. This is the structure for carbon disulfide. Let's go ahead and count electron groups. Remember, doesn't matter if it's a single, double, or triple. This is 1 group or cloud, and this is 1 group or cloud. And there are no lone pairs on the central species. So we have a total of 2 electron groups, which means this is, again, linear. And if you look at a space-filling model here, it shouldn't be any surprise for you to see that the bond angles in linear, triatomic, and diatomic shapes or compounds is a 180-degree bond angle. Now, polarity and hybridization are topics that I'll cover in later videos. Now let's talk about the 3D structure when we have 3 electron groups. And we're going to do some examples here. So I want to point out, when there are 3 electron groups, we refer to them as trigonal planar. However, their bonded atoms will conform to a molecular shape and give a geometry to the molecule. And in this case, there are 2 different molecular shapes for this one electron group shape. So you could have trigonal planar, or trigonal planar bent. Let's look at this example here. Boron trichloride. Okay, boron trichloride. Now I am simply drawing my skeletal structure, acknowledging that these electrons are going to try to minimize repulsion. That's the lowest energy, so I'm kind of spreading them out like that. And let me go ahead and move that down a little bit because it's going to be hard to see. Okay, now I'm going to add my leftover valence electrons to the outer species to satisfy octet rule. And again, boron was one of those exceptions. Boron will have an incomplete octet like beryllium and many times aluminum will. Formal charges on this structure show that this is the correct Lewis structure for boron trichloride. Now, a bit of intuition on the bond angles here. This is think of a circle, okay? And if you were to divide a circle 360 degrees by 3, you would get 120 degrees between the different bonds. And indeed, the ideal bond angle for a trigonal planar molecular shape is 120 degrees. I want you to think about it. A circle divided by 3. That should make sense. And oftentimes I'll implore students to use this as a starting point for trying to determine bond angles on their own without the shape sheet. Again, polarity and hybridization are topics that I'll talk about later. Let's do another example with 3 groups, except this time sulfur dioxide is going to be an example of one that has, well, let's look at it. And again, pause the video, try it on your own. All right, so you are going to add up all your valence electrons, make your skeletal structure, and you're going to find that you need to double up on a bond to make this work. Okay, and if you go through here and look at it, you are left with needing 2. So now we're placing 2 electrons, or 1 lone pair, on the central atom. And remember, a lone pair is an electron group. So let's count groups here. 1 group, 2, 3. Just like up here, I didn't do it, but it's pretty obvious with the trigonal planar shape. So here we have a shape. We have 3 effective pairs. We have 3 electron clouds, but we have an AX2E where we have 1 lone pair and 2 bonded. So what that leads to is an overall bent shape. So if I were to redraw this, I would indicate that there's actually a little bit of an angle. And what's going to happen is this lone pair is going to decrease the ideal bond angle. Take a look at this model here. I want to show you that you have electrons here that are bonded, right? They're being shared, but they're a covalent bond. And then this lone pair up here is able to move around more, okay? Because it's not locked into a bond with another atom. So this lone pair is able to move around more on the central species. So what that means is it has a larger area that it is occupying. Now what that means is that it's pushing down on that ideal 120 bond angle that we saw in trigonal planar. So there's some additional repulsion here of electrons. And what that's doing is it's decreasing our bond angle and making it less than 120. Because there is one lone pair. Now you can imagine if there were two lone pair on the central species, it would be decreasing that angle even more. And we're going to get to examples that show that in the next video. Okay, so in this case here, we had a 117.8 degree bond angle. Now you don't need to know that exact number. You just need to be able to ballpark and for sure understand it will be less than the 120 that we saw in a trigonal planar. So this is a trigonal planar bent structure with bond angles less than 120 degrees. All right, so the last example for this video, let's look at 4 clouds, 4 groups. Methane, okay? So I want you to notice too on your shape sheet. Now we are 4 clouds, but look at there's 3 different molecular shapes. We now have tetrahedral, tetrahedral trigonal pyramidal, and tetrahedral bent. And I'm going to talk about all of them. All right, okay, first let's look at methane here. All right, structure, so skeletal structure here. CH4 in case you've forgotten methane. And you know that hydrogen's good with its 2 electrons or 1 line, and carbon is good. Carbon has a formal charge of 0. The hydrogens have 0. All fulfill, all have a stable valence shell. So this is actually the complete structure for methane. How about ammonia? All right, this one's a little different. So if you go through and do this one, NH3, and you go through and get all of your valence electrons and work all of that out, you're going to end with a lone pair on the central atom. Let's count clouds. 1, 2, 3, 4. That's how many electron groups there are. 1, 2, 3, there's a lone pair, 4, okay? So the last example of a molecular shape within 4 clouds would be an AX2E2 in which there are now 2 lone pairs on that central atom, and I've already alluded to what will occur when that happens. Now, to illustrate and help you conceptualize the 3-dimensional Lewis structures for these 3 examples, I'm going to take you to an online PHET simulation. All right, so we had 3 different molecular shapes for structures that have 4 electron groups. The first one we discussed was methane. I want to show you what the bond angles look like and what the overall 3-dimensional structure looks like so you can better conceptualize the valence shell electron pair repulsion theory and how electrons affect the overall molecular geometry. So for a tetrahedral shape, we're going to have bond angles of 109.5. There's a proof for these bond angles. It's based on trigonometry. It's really cool. And if you're interested in seeing it, talk to me in class. So 109.5, I'll tell students again, remember tetrahedrals, 109.5, and then you can reason from there what other bond angles would be. So you can see now the three-dimensional structure here. All right. Now the next one I want to talk to you about was ammonia. Now ammonia had one lone pair, okay? And if you look at ammonia, you'll see, as I discussed in the examples, that that lone pair is able to move around more. Okay, we saw that in the example with sulfur dioxide. So what is it doing? That lone pair is moving around more and effectively decreasing the bond angle, making it less than 109.5. And in this case, we see 107.8. Now, that's not critical, but what is to me very important is that you can understand that the bond angles with this one lone pair will make it less than 109.5. Now, in the final example, we have water, okay? And I didn't draw this one out for you because I was going to show it to you here. We have two lone pairs on the central species. All right, so now imagine both of those lone pairs moving around that central atom. What are they doing? Decreasing the bond angle even more. So we had a 109.5 for a tetrahedral. And then when we added one lone pair on the central species, we went down or less than, so around 107. And now for water, you can see a bond angle of 104.5, so even less than 107, okay? And that's how this works. Now to save us a little time, I'm gonna close out with this video by stating you can now go through your problem set and assign the molecular shapes to all the structures you worked out in two-dimensional form. I'll see you guys in class.